Stand outside on a clear night and look up at the stars. How far can you see? A few thousand light years, perhaps, to the most distant stars visible to the naked eye. Now imagine having a telescope, a powerful one that can gather more light than your eye. Suddenly you can see millions of light years into space, galaxies upon galaxies, stretching into the cosmic distance. But even the most powerful telescopes have limits. There is a horizon to our observations, a boundary beyond which we cannot see. Not because there is nothing there, but because light from those regions has not had time to reach us since the beginning of the universe. And beyond that horizon, the universe continues, perhaps infinitely, perhaps not, containing regions we can never observe, never visit, never know anything about, except through theoretical speculation. How big is the universe? This is one of the most profound questions we can ask, touching on physics, cosmology, philosophy, and the very limits of human knowledge. The answer depends on what we mean by the universe. Do we mean the observable universe, the region of space from which light has had time to reach us? Or do we mean the entire universe, including regions beyond our cosmic horizon? And is the universe finite or infinite in extent? These questions have different answers, and some have no definitive answers at all, only estimates and possibilities constrained by our observations and theories. Let us begin with what we can measure, the observable universe. This is the spherical region of space centered on Earth, from which light has had time to reach us since the Big Bang. The universe is nearly 14 billion years old, so you might think the observable universe has a radius of nearly 14 billion light years. But this is not correct, because the universe has been expanding during the time light has been traveling toward us. Space itself has been stretching, carrying distant objects farther away, even as their light moves toward us. By the time light from a distant galaxy reaches us, that galaxy has moved to an even greater distance due to cosmic expansion. When we account for expansion, the radius of the observable universe is about 46.5 billion light years, making the diameter roughly 93 billion light years. This is the moving distance, the distance to the most distant objects whose light is reaching us now, accounting for how far those objects have moved due to expansion during the time their light has been traveling. This is an enormous distance, far larger than the age of the universe in light years would suggest, a testament to how much space has expanded over cosmic history. But even this number understates the scale, because we are not talking about a line, but a volume. The observable universe is a sphere with a radius of 46.5 billion light years, and the volume of a sphere grows with the cube of the radius. If we calculate the volume of the observable universe, it comes to an incomprehensibly large number of cubic meters, so large it loses all intuitive meaning. To put it in perspective, if you could count 1 cubic meter per second, it would take you far longer than the age of the universe to count them all. The observable universe is not just big, it is incomprehensibly vast. And this is just the part we can see. The entire universe, the whole of physical reality, is likely much larger, possibly infinitely larger. The observable universe is just the region within our cosmic horizon, the region from which light has had time to reach us. Beyond this horizon, the universe continues, filled with more galaxies, more stars, more space stretching on and on. We cannot see these regions, and we never will, because light from them has not had time to reach us, and never will, due to the accelerating expansion of space. But they are just as real as the part we can observe. They are part of the same universe, governed by the same laws of physics, containing the same types of structures, galaxies, stars, planets, perhaps even life. How much larger is the entire universe compared to the observable universe? We do not know. It could be just slightly larger, or it could be infinitely larger. Observations of the cosmic microwave background radiation suggest that the universe is very close to spatially flat, which in the context of general relativity implies that the universe might be infinite in extent. If the universe is perfectly flat, it extends forever in all directions, containing infinite space, infinite matter, infinite galaxies, infinite stars, infinite everything. This is a mind-bending concept, and we should take a moment to consider what it means. An infinite universe is not just very large. It is unbounded, having no edge, no center, no outside. No matter how far you travel in any direction, you never reach a boundary. There is always more space, more galaxies, more structure stretching away from you in all directions. You can never see all of it, never map all of it, never comprehend all of it, because it is literally endless. This is difficult to visualize because we have no experience with infinity in the physical world. Everything we encounter in daily life is finite sizes, finite distances, finite numbers. But the universe might be the one thing that truly is infinite, not as a mathematical abstraction, but as a physical reality. If the universe is infinite, then it contains everything that is physically possible. Somewhere infinitely far away, there is another galaxy identical to the Milky Way. Somewhere there is another solar system identical to ours, with a planet identical to Earth, where someone identical to you is reading these exact words. This is not speculation, but a mathematical consequence of infinity. If space is infinite and matter is distributed throughout it with some degree of randomness, then every possible configuration of matter will occur somewhere and will occur infinitely many times. There are infinite copies of you, living lives identical to yours up to this moment, and other copies living lives that diverge from yours in small or large ways. This is deeply strange and counterintuitive. It challenges our notion of individuality and uniqueness. If there are infinite copies of you, in what sense are you unique? Which one is the real you? The answer is that they are all equally real, all equally you in some sense, all experiencing their own version of reality. The concept of a unique individual breaks down in an infinite universe. You are not one person, but an infinite ensemble of people, all sharing your history up to some point, all diverging in the details of their lives thereafter. But is the universe really infinite? The observations are consistent with an infinite universe, but they do not prove it. The universe could be finite, but very large, so large that the part we can observe looks flat within the precision of our measurements. Imagine you are standing on a planet the size of the observable universe. The surface would look flat to you, even though it is actually curved into a sphere. You would need to travel vast distances far beyond what you can see to detect the curvature. Similarly, the universe could be finite, but so large that its curvature is undetectable within the observable universe. If the universe is finite, it could have a variety of topologies, different global shapes. It could be a three-dimensional sphere curving back on itself so that if you travel far enough in one direction, You eventually return to your starting point, like traveling around Earth's surface. It could be a torus shaped like a donut in higher dimensions, with wraparound geometry where opposite edges are connected. It could have more exotic topologies, multiply, connected, or twisted in ways that have no analog in our everyday experience. These different topologies would have observable consequences, patterns in the cosmic microwave background, for instance, or repeated images of distant galaxies. So far, no such patterns have been detected, suggesting either that the universe is infinite or that it is finite, but larger than the observable universe, so we cannot see the topological features. The question of whether the universe is finite or infinite is not just academic. It touches on deep philosophical issues about the nature of existence and the limits of knowledge. If the universe is infinite, then there are regions we can never observe, facts we can never know, questions we can never answer empirically. The unobservable parts of the universe are forever beyond our reach, separated from us not by mere distance, but by the structure of space-time itself. This imposes a fundamental limit on science, a boundary to what we can discover through observation. Beyond that boundary, we can only speculate, reason, hypothesize, but never confirm. Yet, even if we cannot observe the entire universe, we can still reason about it. The laws of physics we have discovered through local experiments and observations presumably apply everywhere, not just in the observable universe, but throughout all of space. Gravity, electromagnetism, quantum mechanics, these are not local phenomena, but universal principles. If they apply here, they apply everywhere, even in regions we cannot see. This universality of physical law is an assumption, but a well-supported one. The universe appears to be the same everywhere we look, the same structures and processes operating according to the same rules. There is no reason to think this changes beyond our horizon. This universality is itself remarkable. Why should the laws of physics be the same everywhere? Why should the universe be uniform on large scales? These are not trivial facts, but profound features of reality that demand explanation. One answer comes from cosmic inflation, the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched a tiny region of space, smaller than an atom, to a size much larger than the observable universe today. This tiny region was uniform because it was so small that quantum fluctuations could smooth out any variations. When inflation expanded this region to cosmic scales, it carried this uniformity with it, creating a universe that is nearly the same everywhere. Inflation also explains why the universe appears flat. During exponential expansion, any initial curvature would have been diluted, stretched out until space appears flat, just as the surface of a balloon appears flatter and flatter as it inflates. If inflation is correct, the universe is probably much larger than the observable universe, perhaps infinite, and it is flat or very nearly flat on scales larger than we can observe. The observable universe is just a tiny patch of a much larger inflated region, and that region might be just one of many in an even larger multiverse. Within the observable universe, matter is not distributed uniformly, but organized into a cosmic web, a vast structure of filaments and voids that spans the entire visible cosmos. Galaxies are not scattered randomly, but clustered along filaments, threads of matter connecting dense nodes where galaxy clusters reside. Between the filaments are voids, enormous empty regions hundreds of millions of light years across, containing few galaxies. This cosmic web is the largest structure in the universe, the scaffolding on which all smaller structures hang. The cosmic web formed through gravitational instability, amplifying tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter, growing denser over time, while regions that were slightly less dense lost matter and became voids. Over billions of years, this process carved the universe into the web-like structure we see today. The filaments are rivers of dark matter, with galaxies forming where the dark matter is densest. The entire structure is held together by gravity, a vast gravitational architecture spanning the observable universe. To understand the scale of the cosmic web, consider the largest structures within it. The largest galaxy clusters contain thousands of galaxies and span tens of millions of light years. These clusters are gravitationally bound, held together by their mutual gravity despite the expansion of the universe. The Virgo cluster, for instance, is a massive cluster about 65 million light years away, containing over 1,000 galaxies. Our own local group of galaxies is part of the Virgo supercluster, an even larger structure, about 110 million light years across, containing the Virgo cluster and many smaller groups of galaxies, including ours. But even superclusters are not the largest structures. The cosmic web extends beyond individual superclusters, connecting them into vast walls and filaments. The Sloan Great Wall is a vast structure of galaxies, about 1.4 billion light years long, one of the largest known structures in the universe. More recently, astronomers have identified even larger structures, like the Hercules Corona Borealis Great Wall, a possible structure over 10 billion light years across, though its existence as a single coherent structure is debated. These structures are so large that light takes billions of years to travel from one end to the other, comparable to significant fractions of the age of the universe. How can structures so large exist? In the early universe, matter was distributed almost uniformly, with density variations of only a few parts in 100,000. Gravity has been working to amplify these variations for nearly 14 billion years, but that is not enough time to create structures 10 billion light years across from gravitational collapse alone. These structures did not form by collapse, but by the original distribution of density fluctuations in the early universe. The cosmic web reflects the pattern of quantum fluctuations from the inflationary era, stretched to cosmic scales and amplified by gravity. The largest structures in the universe are fossils from the first moments after the Big Bang, patterns imprinted when the universe was smaller than an atom, now visible across billions of light years. This connection between the very small and the very large is one of the most beautiful aspects of modern cosmology. The universe is a unified system where processes at the smallest scales influence structures at the largest scales. Quantum fluctuations in the inflating early universe seeded the cosmic web. The behavior of subatomic particles determines the fate of stars and galaxies. The properties of atoms dictate the chemistry of planets and the possibility of life. There is a deep interconnectedness running through the cosmos, linking the quantum realm to the cosmic, the microscopic to the macroscopic. Understanding the universe requires understanding all these scales and how they relate to each other. Let us zoom in from the cosmic web to the scale of galaxy clusters, then to individual galaxies, then to stars, and finally to planets, human scales, and beyond, down to atoms and subatomic particles. This journey through scales will help us appreciate the full range of sizes in the universe, from the largest structures to the smallest particles, and the vast range of scales over which physical processes operate. A galaxy cluster like the Virgo cluster spans about 15 million light-years and contains thousands of galaxies. Within such a cluster, galaxies move through space at hundreds or thousands of kilometers per second, held in orbit by the cluster's gravity. The space between galaxies is not empty but filled with hot gas, heated to millions of degrees by the energy released as galaxies fall into the cluster and as matter accretes onto the cluster over cosmic time. This gas is so hot it emits X-rays, making galaxy clusters some of the brightest X-ray sources in the universe. Within a galaxy cluster, we find individual galaxies like our Milky Way, spirals of stars about 100,000 light-years across, containing hundreds of billions of stars. Each galaxy is a complex system with its own internal structure, a central bulge, a disk with spiral arms, a halo of old stars, and dark matter. Galaxies rotate, with stars orbiting the galactic center, taking hundreds of millions of years to complete one orbit. The Milky Way rotates, the Sun orbiting the galactic center at about 220 kilometers per second, completing one orbit every 225 to 250 million years. Within a galaxy, we zoom in on stellar systems, stars with their planets, moons, asteroids, and comets. Our solar system spans about 100,000 astronomical units if we include the Oort cloud, or about 1.5 light-years, a tiny region compared to the galaxy, but still vast on human scales. The distance from the Sun to Earth, 1 astronomical unit, is about 150 million kilometers, or about 8 light minutes. Light from the Sun takes 8 minutes to reach Earth, so we see the Sun as it was 8 minutes ago. On planetary scales, Earth is about 12,700 kilometers in diameter, a rocky sphere with a thin atmosphere, mostly water-covered, with continents and oceans and a biosphere teeming with life. Humans are about 1.7 meters tall on average, and our everyday experience involves distances of meters to kilometers, timescales of seconds to years. This is the scale on which our intuitions are calibrated, the scale where we live and work and perceive the world directly. But we can go smaller. Zoom in on your hand, and you see it is made of cells, about 10 micrometers in size. Each cell is a complex factory containing organelles, membranes, proteins, all working together to maintain life. Zoom in further, and you reach molecules, a few nanometers in size. A molecule of DNA, the blueprint of life, is a double helix about 2 nanometers wide, encoding information in the sequence of its base pairs. Zoom in more, and you reach atoms, about 0.1 nanometers across, the basic units of matter, consisting of a nucleus surrounded by a cloud of electrons. The nucleus is much smaller than the atom, about 10,000 times smaller, just a few femtometers across. If an atom were the size of a stadium, the nucleus would be the size of a marble at the center. Yet the nucleus contains almost all the atom's mass, a dense core of protons and neutrons held together by the strong nuclear force. Zoom in even further, and you reach quarks, the constituents of protons and neutrons and electrons, fundamental particles with no known internal structure, existing at scales smaller than anything we can currently measure. the limits of our experimental resolution. So we have traveled from the cosmic web, structures 10 billion light years across, down to quarks and electrons, particles smaller than anything we can probe. The ratio of these scales is about 100,000 trillion, a factor incomprehensibly large. This is the range of scales on which physical processes operate, from the cosmological to the quantum, and somehow all these scales are connected, governed by the same fundamental laws of physics. This range of scales is so vast that our minds cannot truly grasp it. We can write down the descriptions, we can calculate the ratios, but we cannot visualize or intuit what it means for something to be so vastly larger than something else. Our brains evolved to deal with scales from millimeters to kilometers, time scales from milliseconds to decades. Anything much smaller or larger than this is beyond our intuitive grasp. We can only approach these scales through abstraction, mathematics, and analogies that map the incomprehensible onto the familiar. One useful analogy is to scale the universe down so that we can fit all these scales into our mind simultaneously. Imagine we shrink the observable universe down to the size of Earth. On this scale, the Milky Way would be about the size of a small house. The solar system would be invisible, smaller than a single cell. The sun would be smaller than an atom. A human would be far smaller than a quark, vanishingly tiny, almost a mathematical point. This gives a sense of how small we are compared to the cosmos, but it also shows the range of scales in the universe, from the largest structures down to the smallest particles, all part of one interconnected reality. Another way to think about scales is through powers of 10, moving up or down by factors of 10 at each step. Starting at 1 meter, the human scale, we can go up. 10 meters is the size of a house, 100 meters the length of a football field, 1 kilometer the distance you might walk, 10 kilometers a short drive, 100 kilometers the distance between cities, 1,000 kilometers the scale of large countries, 10,000 kilometers the diameter of Earth, 100,000 kilometers the distance to the Moon, 1 million kilometers the scale of planetary orbits, 10 million kilometers the inner solar system, 100 million kilometers the distance from Earth to the Sun. Continuing upward, 1 billion kilometers the scale of the outer solar system, 10 billion kilometers the realm of the Kuiper belt, 100 billion kilometers the distance to the Oort cloud. 1 trillion kilometers is about 0.1 light years. 10 trillion kilometers is 1 light year. 100 trillion kilometers is 10 light years, getting us to the nearest stars. Keep going. 1 million trillion kilometers is 100,000 light years, the size of the Milky Way. 10 million trillion kilometers is 1,000,000 light years, the scale of the local group of galaxies. 100 million trillion kilometers is 10 million light years, the scale of galaxy clusters, and so on, up to the observable universe at unimaginable distances. Going down from 1 meter, 0.1 meters is 10 centimeters, the size of your hand. 0.01 meters is 1 centimeter, the width of a finger. 0.001 meters is 1 millimeter, the size of a grain of sand. 0.0001 meters is 100 micrometers, the width of a human hair. 0.00001 meters is 10 micrometers, the size of a cell. Continuing downward through ever smaller scales, 1 micrometer, the size of bacteria. 100 nanometers, the wavelength of ultraviolet light. 10 nanometers, the size of large molecules. 1 nanometer, the size of atoms. Continue downward. 0.1 nanometers, the size of an atom; 10 picometers, the scale of atomic nuclei; 1 picometer; 100 femtometers, 10 femtometers, the size of a proton; 1 femtometer. Below this, we enter the realm of quarks and electrons, and we reach the limits of current experimental physics at scales we can barely probe. So from 1 meter, we can go up many orders of magnitude to reach the observable universe, and down many orders of magnitude to reach the smallest particles we have detected. This is a span of many orders of magnitude, incomprehensibly large. The universe spans an incomprehensible range of scales, and we, at about 1 meter in size, sit roughly in the middle of this range, able to perceive and understand both the very large and the very small, at least in principle. But there are theoretical reasons to think that physical scales extend beyond what we have observed. On the small end, we might expect quantum gravity effects to become important at the Planck scale, far smaller than anything we can currently probe experimentally. At this scale, space-time itself might become quantized, breaking down into discrete units rather than being smooth and continuous. The Planck length is the scale where quantum mechanics and gravity are both important, where the uncertainty in the position of a particle is comparable to its Schwarzschild radius, making it a black hole. Below the Planck length, our current theories of physics break down, and we need a theory of quantum gravity to describe what happens. On the large end, the observable universe is just a part of the universe we can see. The entire universe might be much larger, possibly infinite. And if the multiverse hypothesis is correct, our universe might be just one bubble in an enormously larger multiverse, with other universes beyond ours, each perhaps infinite in its own right. The scales could extend indefinitely upward, level after level of structure and organization, far beyond the observable universe. This possibility of a multiverse brings us back to the question of how big the universe is. If we live in a multiverse, then the answer depends on whether we mean our universe or the multiverse as a whole. Our universe, the region of space-time that emerged from our Big Bang and is governed by our physical constants, might be finite or infinite. But the multiverse, the totality of all universes, could be vastly larger, perhaps infinitely larger, containing infinite universes, each infinite in extent, each with its own laws of physics, its own structures, its own history. The multiverse hypothesis arises from several independent lines of theoretical reasoning. Cosmic inflation, which explains many features of the observable universe, naturally leads to eternal inflation, where inflation continues forever in some regions, creating an infinite number of bubble universes, each with its own Big Bang. String theory, a candidate theory of quantum gravity, suggests a vast landscape of possible universes with different physical constants, all potentially realized somewhere in the multiverse. The many worlds interpretation of quantum mechanics implies that every quantum event causes the universe to branch into multiple realities, creating a multiverse of quantum possibilities. If the multiverse exists, it has profound implications for the question of how big the universe is. It means that our observable universe, vast as it is infinitesimally small compared to the totality of reality. It means that the structures we observe, galaxies, stars, planets, are not unique, but repeated countless times in other universes. It means that the physical constants we measure, which appear fine-tuned for life, are not fundamental, but environmental, varying from universe to universe. And it means that there are regions of the multiverse we can never observe, never visit, never interact with, not because they are far away, but because they are causally disconnected from us by the structure of space-time. Yet the multiverse hypothesis remains speculative. We have no direct evidence for other universes, and by their nature, they might be unobservable. This raises philosophical questions about whether the multiverse is a scientific hypothesis at all, or whether it is metaphysics masquerading as physics. Can we accept the existence of something we can never observe? Should we invoke infinite, unobservable universes to explain the properties of the one we can see? These are contentious questions, and physicists and philosophers disagree on the answers. But whether or not the multiverse exists, the observable universe is already unimaginably vast. Let us return to concrete measurements and observations to appreciate this vastness. The observable universe contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars on average. This gives a total of about 1 trillion stars in the observable universe, a number with 24 zeros, incomprehensibly large. If each star has even one planet on average, there are at least as many planets. The number of atoms in all these stars and planets is about a number with 80 zeros, a number so large it dwarfs all other large numbers we normally encounter. To put this in perspective, the number of seconds since the Big Bang is much smaller than the number of stars. The number of grains of sand on all the beaches on Earth is estimated at a large but finite number, still far smaller than the number of stars. The number of atoms in a human body is larger than the number of stars, but still much smaller than the number of atoms in the observable universe. These comparisons show that the universe contains numbers of objects that are incomprehensibly large, far beyond anything in human experience. Yet even these numbers understate the scale of the universe in another sense, the volume of space. Most of the observable universe is empty space, vast regions containing no matter, no energy, nothing but the fabric of space-time itself and the quantum fields that pervade it. The distances between stars, between galaxies, between galaxy clusters are enormous compared to the sizes of the objects themselves. Space is mostly empty, and the universe is mostly space. Consider the Sun, a sphere about 1.4 million kilometers in diameter. The nearest star, Proxima Centauri, is about 40 trillion kilometers away, or about 4.2 light years. If the Sun were the size of a grain of sand, Proxima Centauri would be another grain of sand about 4 kilometers away. The space between them would be almost entirely empty, traversed only by the faint light and particles emanating from each star. This is the typical spacing between stars in our galaxy. Vast emptiness punctuated by tiny points of matter and energy. On larger scales, galaxies are separated by even greater voids. The Milky Way and the Andromeda Galaxy, our nearest large neighbor, are about 2.5 million light years apart. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 20 meters away. The space between them is not entirely empty. It contains some gas and dust, some dark matter, perhaps a few rogue stars, but it is mostly vacuum, far more empty than the space between stars. On the scale of galaxy clusters in the cosmic web, the voids are even more pronounced. The voids in the cosmic web span hundreds of millions of light years, and contain almost no galaxies, just diffuse gas and dark matter. These voids are the largest empty spaces in the universe, vast regions where matter is absent or extremely sparse. If you were placed at random in the observable universe, the odds are overwhelming that you would find yourself in one of these voids, far from any galaxy, surrounded by darkness and emptiness. The regions where matter is concentrated, galaxies, stars, planets, are rare exceptions, tiny oases in a vast desert of space. This emptiness is not a defect or a lack, but a fundamental feature of the universe. The expansion of space creates distance, and gravity pulls matter together into localized structures, leaving most of space empty. This is a natural result of the interplay between expansion and gravity, the two main forces shaping the large-scale structure of the universe. Expansion dilutes matter, spreading it thinner over time, while gravity counteracts expansion locally, pulling matter into dense structures. The result is a universe that is mostly empty, but contains dense pockets of matter and energy. The emptiness also means that the universe is silent and dark. Most of space is far from any star, receiving only the faint glow of distant galaxies and the cosmic microwave background radiation. If you were floating in intergalactic space far from any galaxy, the sky would be almost entirely black, with only the faintest smudges of light marking the locations of distant galaxy clusters. You would be surrounded by a profound silence and darkness, broken only by the faint whisper of the cosmic microwave background, the afterglow of the Big Bang, filling all of space with its cold radiation. This darkness and silence are in stark contrast to the sky as we see it from Earth. Here we are inside a galaxy, surrounded by stars, bathed in the light of the sun during the day and the light of countless stars at night. We live in one of the rare regions where matter is concentrated, where light and energy are abundant. This is not a coincidence. Life requires energy, and energy is concentrated around stars. We find ourselves in a bright region because only bright regions can support life. The vast empty regions of the universe are dark and silent precisely because they are inhospitable to life. But even from Earth, when we look out into the universe, most of what we see is empty space. When we look at a galaxy, we see a collection of stars, but the stars are separated by vast emptiness. When we look at a galaxy cluster, we see galaxies, but the galaxies are separated by intergalactic space. When we look at the cosmic web, we see filaments of galaxies, but the filaments are separated by voids. At every scale, the universe is more empty than full, more space than matter, more darkness than light. This raises a philosophical question. Why does the universe contain anything at all? Why is it not just empty space or nothing at all? The existence of matter and energy, of structure and complexity, is not inevitable. The laws of physics allow for a universe that is essentially empty, containing only the cosmological constant and the vacuum energy of empty space. Yet our universe contains galaxies, stars, planets, life, consciousness. How did this complexity arise from the simplicity of the early universe? The answer lies in the tiny density fluctuations present in the early universe, imprinted during cosmic inflation and visible in the cosmic microwave background. These fluctuations were incredibly small, just a few parts in 100,000, but they were enough. Gravity amplified these tiny variations over billions of years, pulling matter together into increasingly dense structures. Small fluctuations became proto-galactic clouds, which collapsed into galaxies, which fragmented into star clusters, which formed individual stars, which produced planets, which eventually, on at least one planet we know of, gave rise to life and consciousness. The chain of causation from quantum fluctuations to conscious observers is long and intricate, involving nuclear physics, chemistry, geology, biology, and countless other processes. But it is an unbroken chain, connecting the largest scales to the smallest, the earliest times to the present moment. The universe is a unified system where initial conditions, physical laws, and chance events interact to produce the structures we observe. Understanding how this works, how the universe went from nearly uniform simplicity to hierarchical complexity, is one of the great achievements of modern science. And yet, for all we have learned, the question of size remains partially unanswered. We can measure the observable universe, but we cannot measure the entire universe. We can estimate distances to distant galaxies, but we cannot see beyond the cosmic horizon. We can theorize about the multiverse, but we cannot confirm its existence. The universe guards its ultimate extent as a secret, perhaps forever beyond our reach. This limitation is not just practical, but fundamental, rooted in the finite speed of light and the finite age of the universe. There is a horizon to our observations, a boundary beyond which we cannot see because light from those regions has not had time to reach us. This horizon is not a physical barrier, but an informational one. Information from beyond the horizon has not arrived yet, and might never arrive if the expansion of space continues to accelerate. We are limited not just by our technology, but by the structure of space-time itself. Some physicists have suggested that this limit is not absolute, that we might find indirect evidence for regions beyond our horizon. If the universe has a non-trivial topology, for instance, we might see repeated patterns in the cosmic microwave background, signatures of the wraparound structure of space. If cosmic inflation left imprints on the distribution of matter, we might detect those imprints and infer properties of the larger universe. If the multiverse exists, collisions between our universe and others during the inflationary era might have left marks in the cosmic microwave background. These are speculative ideas, but they suggest that the unobservable might not be entirely beyond our reach, that clever reasoning and careful observations might reveal hints of the larger reality beyond our horizon. But even if we can never observe the entire universe directly, we can still reason about it. The laws of physics we have discovered through local experiments presumably apply throughout the universe, and these laws constrain what is possible. If the universe is infinite, it must be infinite in specific ways, consistent with the equations of general relativity and quantum mechanics. If the multiverse exists, it must have a structure consistent with the theories that predict it. We are not entirely ignorant about the unobservable universe. We can infer its properties from the part we can see and from the theories that describe both. This is the power of science, to extend our knowledge beyond our direct experience through reasoning, mathematics, and the assumption that nature is consistent. We cannot see quarks, but we can infer their existence from particle collisions. We cannot see dark matter, but we can infer its presence from gravitational effects. We cannot see beyond the cosmic horizon, but we can infer properties of the larger universe from its visible portion. Science is not limited to the directly observable, but extends through inference to the indirectly knowable. Yet there remains a limit to this process. Some questions might be forever unanswerable. not because we lack clever ideas, but because the information needed to answer them is unavailable. If the universe is infinite, we can never survey all of it. If the multiverse exists, we can never visit other universes. If there are physical processes beyond the Planck scale, we might never probe them experimentally. There is a boundary to human knowledge, a horizon beyond which lies the permanently unknowable. This should give us humility. We have learned an enormous amount about the universe, but there is much we do not know, and perhaps much we can never know. The universe is vast and complex, and we are small and limited. Our knowledge is impressive but partial, our understanding deep but incomplete. The question of how big the universe is has no simple answer, because the universe is more complex, more subtle, more extensive than any simple answer can capture. But this should also give us hope. The fact that questions remain unanswered means there is more to discover, more to understand, more to explore. Science is not finished, but ongoing, an endless frontier pushing against the boundaries of the known. Each answer raises new questions. Each discovery reveals new mysteries. The universe continually surprises us, challenging our expectations and forcing us to revise our theories. This is the beauty of science. It is a process, not a product, a journey without a final destination. So how big is the universe? The observable universe is about 93 billion light-years in diameter, containing about 2 trillion galaxies and 1 trillion stars. The entire universe is at least this big, possibly much bigger, perhaps infinite. The multiverse, if it exists, is vastly larger still, containing infinite universes, each possibly infinite in extent. The range of scales in the universe spans from quarks at unimaginably small scales to the observable universe at unimaginably large scales, a factor incomprehensibly vast. And all of this structure, all of this complexity, arose from quantum fluctuations in the first fraction of a second after the Big Bang, amplified by gravity over nearly 14 billion years. The universe is unimaginably vast, incomprehensibly complex, and profoundly mysterious. It is the ultimate frontier, the grandest puzzle, the deepest mystery we face. And we, tiny creatures on a small planet orbiting an ordinary star in an ordinary galaxy, have managed to measure it, map it, understand it, at least partially. This is an extraordinary achievement, a testament to the power of human curiosity and intelligence. We are small, but we are also mighty. We can comprehend the universe, even if we cannot encompass it. As you contemplate these scales, these distances, these vast numbers, let yourself feel both the immensity of the cosmos and the wonder of your place within it. You are part of this vast universe, made of its matter, governed by its laws, shaped by its history. You are connected to the furthest galaxies through the fabric of space-time, to the earliest moments through the atoms in your body, to the largest structures through the cosmic web that spans the observable universe. You are not separate from the cosmos, but embedded in it, a small part of an incomprehensibly large whole. And yet you are also special. You are conscious, aware, able to ask questions about the universe, and to understand at least some of the answers. You are one of the rare structures in the universe that can contemplate the universe itself, that can measure its size and ponder its origins and wonder about its ultimate fate. The universe is vast, but you are the part of the universe that knows it is vast. This is a remarkable role, even if you are small. You are the universe becoming conscious of itself, matter organizing itself into patterns complex enough to reflect on its own existence. So how big is the universe? It is bigger than you can imagine, yet small enough that you can hold a picture of it in your mind. It is finite in the parts you can observe, yet possibly infinite in extent. It is full of structure and complexity, yet mostly empty space. It is ancient beyond comprehension, yet still young in cosmic terms. It is knowable through science, yet fundamentally mysterious in its deepest aspects. It is all of these things at once, a paradox and a wonder, the ultimate subject of human inquiry. Rest now in this knowledge, let it settle into your consciousness, like sediment falling through water, slowly clarifying your view. The universe is vast, and you are part of it. That is enough for now. Tomorrow there will be new questions, new observations, new theories, new mysteries to explore. But tonight, simply be a conscious being in a vast cosmos, briefly aware of your place in the grand scheme of things. The universe has been here for nearly 14 billion years, and it will be here for trillions more. You are here for a brief moment, a flicker of awareness in the cosmic darkness. Make the most of it. Wonder at it, appreciate it, and know that you are part of something incomprehensibly large and beautiful, something that stretches from the smallest quarks to the furthest reaches of space, from the first moment of time to the distant future, from the known to the unknown, from the observable to the infinite. This is the universe, and you are part of it. How big is it? Big enough to contain you, and that is all that matters. Yet let us not end our contemplation here, for there are more dimensions to explore, more perspectives from which to view the vastness that surrounds us. The question of size is not merely about spatial extent, but also about time, about the duration and evolution of cosmic structures, about the deep history that has led to this moment and the incomprehensibly long future that awaits. Consider the age of the universe itself, nearly 14 billion years, stretching back to the Big Bang. This duration is so vast that human timescales shrink to insignificance against it. All of recorded human history, from the earliest civilizations to the present day, spans perhaps 10,000 years, less than 1/1,000,000th of cosmic history. Our species has existed for only a few 100,000 years, barely a flicker in cosmic time. Even life on Earth, which began nearly 4 billion years ago, represents only about 1/4 of the universe's total age. But the past is just prologue. The future of the universe will dwarf its past. Stars will continue to shine for trillions of years. The smallest, dimmest red dwarf stars burn their fuel so slowly that they could last 100 times longer than the current age of the universe. By the time the last of these stars finally exhausts its fuel and fades to darkness, the universe will have aged beyond recognition. The cosmic microwave background will have cooled to temperatures barely above absolute zero. The accelerating expansion of space will have carried distant galaxies so far beyond our cosmic horizon that no trace of them remains visible. In this distant future, if any observers exist, they will see a universe vastly different from the one we inhabit. They will see only their own galaxy, or perhaps a merged collection of nearby galaxies gravitationally bound together, surrounded by absolute darkness. The expansion of space will have carried everything else beyond the cosmic horizon, leaving these future observers in a universe that appears static, eternal, and small. They will have no evidence of the Big Bang, no expanding universe to observe, no distant galaxies to study. Their observations will lead them to conclude that the universe is much smaller and simpler than it actually is, a false picture of reality caused by the limitations of their observational horizon. This future scenario is both sobering and illuminating. It reminds us that our current privileged position in cosmic history is temporary. We live in an era when the evidence for the universe's true nature is still visible, when we can observe the cosmic microwave background, when distant galaxies reveal the expansion of space, when the large-scale structure of the cosmos is still within our observational reach. This evidence will not be available forever. Future observers, if any exist, will have lost access to crucial information about the universe's origin and evolution. This raises a profound question. Might there be evidence that was once available but is no longer accessible to us? Could the universe have a prehistory, a complex sequence of events before the Big Bang, whose evidence has been erased by inflation or by the passage of time? Could there be structures at scales larger than the observable universe, forever beyond our horizon, that we can never detect? The answer is almost certainly yes. The universe likely contains secrets that are permanently hidden from us, not because we lack clever observational techniques, but because the information itself has been destroyed or placed beyond the reach of light. This epistemological limit is fundamental. There are questions about the universe that we may never be able to answer, not because they are meaningless or ill-formed, but because the evidence needed to answer them simply does not exist within our accessible region of space-time. This should inspire both humility and determination. Humility because it reminds us of the limits of human knowledge. Determination because it challenges us to extract every possible insight from the evidence we do have. Let us turn now to the concept of cosmic horizons in more detail. There are actually several different types of horizons in cosmology, each defining a different boundary to our knowledge. The particle horizon marks the boundary of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang. This horizon grows with time as light from more distant objects arrives, but it does not grow as fast as one might expect, because the universe's expansion affects how we measure distances. Then there is the event horizon, which in an accelerating universe like ours marks the boundary of the region we will ever be able to observe, even if we wait forever. Because the expansion of space is accelerating, driven by dark energy, there are objects we can see today whose future we will never observe. The light they are emitting right now will never reach us, because the space between us and them is expanding faster than light can traverse it. These objects will fade from view over cosmic time, receding beyond our event horizon into permanent invisibility. The existence of event horizons in cosmology is strange and unsettling. It means that there are parts of the universe with which we can never interact, not even in principle. We cannot send signals to objects beyond the event horizon, nor can we receive signals from them. They are causally disconnected from us, existing in a region of space-time that is, for all practical purposes, a separate reality. The universe is divided into causally connected regions, and we can only ever know about our own region. This causal structure has profound implications for the notion of the universe as a unified whole. If different regions cannot communicate or interact, in what sense do they belong to the same universe? Perhaps the universe is better thought of as a collection of causally disconnected domains, each a universe unto itself, unable to influence or be influenced by the others. This fragmentation of the cosmos into separate domains is a natural consequence of cosmic expansion, especially when that expansion is accelerating. Now consider the nature of time itself at cosmic scales. We often think of time as a universal backdrop against which events occur, ticking away uniformly everywhere. But relativity teaches us that time is not absolute. Different observers, moving at different speeds or situated in different gravitational fields, experience time at different rates. This relativity of time becomes crucial when discussing the size and age of the universe. When cosmologists say the universe is nearly 14 billion years old, they mean according to a specific notion of time called cosmic time or moving time. This is the time measured by observers who are at rest with respect to the cosmic microwave background, who see the universe as isotropic and homogeneous on large scales. But observers moving at high velocities or near intense gravitational fields would measure time differently. For them, the age of the universe might be different. This relativity of time also means that simultaneity is not absolute. There is no universal now that applies throughout the universe. Different observers will disagree about which distant events are happening now, which are in the past, and which are in the future. When we ask how big the universe is right now, we are implicitly assuming a notion of simultaneity that allows us to define what right now means for the entire universe. But this notion is conventional, not absolute. Different observers could slice space-time in different ways, defining different notions of simultaneity, and arrive at different answers for the current size of the universe. This dependence of size on reference frame and simultaneity convention is not just a technical detail, but a fundamental feature of relativistic cosmology. It tells us that the universe does not have an intrinsic, observer-independent size at a given moment. Size is relative, depending on how we choose to measure it, and from what reference frame we make the measurement. This does not mean that size is arbitrary or meaningless, but it does mean that we must be careful to specify our assumptions when discussing cosmic scales. Let us explore another dimension of cosmic vastness, the diversity and complexity of structures within the universe. The universe is not simply large in extent, but also rich in variety, containing structures organized at many different levels and exhibiting an astonishing range of phenomena. At the largest scales, we have already discussed the cosmic web, the intricate network of filaments and voids that spans the observable universe. This structure is the result of gravitational amplification of primordial density fluctuations over billions of years. It represents the large-scale organization of matter in the universe, shaped by the interplay of gravity, dark matter, and the expansion of space. Zooming in, we find galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies. These clusters are among the most massive structures in the universe, containing not only galaxies but also vast quantities of hot gas that fills the space between galaxies. This intercluster medium is heated to tens of millions of degrees by the gravitational energy released as galaxies fall into the cluster. The hot gas emits X-rays, making galaxy clusters bright X-ray sources and allowing us to study them across cosmic distances. Within galaxy clusters, individual galaxies come in a remarkable variety of forms. There are spiral galaxies like our Milky Way, with flat, rotating disks, spiral arms, and active star formation. There are elliptical galaxies, more spherical or elongated in shape, containing mostly old stars with little ongoing star formation. There are irregular galaxies, lacking clear structure, often the result of gravitational interactions or mergers. There are dwarf galaxies, much smaller than the Milky Way, some containing only a few million stars. And there are exotic objects like active galactic nuclei, where supermassive black holes at galactic centers consume matter at prodigious rates, emitting more energy than entire galaxies of stars. Each galaxy is itself a complex system containing not only stars but also gas, dust, and dark matter. The interstellar medium within galaxies is a dynamic environment where new stars form from collapsing clouds of gas and dust, where massive stars end their lives in supernova explosions that enrich the medium with heavy elements, where stellar winds and radiation pressure shape the distribution of gas. Galaxies are not static collections of stars, but evolving systems where matter cycles between different forms over billions of years. Within galaxies, we find an incredible diversity of stellar systems. Our Sun is accompanied by a family of planets, moons, asteroids, and comets, forming a solar system that has existed for over 4.5 billion years. But not all stars have planets, and among those that do, the variety is astounding. We have discovered planets orbiting other stars in nearly every imaginable configuration. Giant planets orbiting close to their stars, smaller rocky planets in the habitable zones where liquid water could exist, planets orbiting binary star systems, planets around neutron stars and white dwarfs, free-floating planets wandering through interstellar space without any star at all. The discovery of these exoplanets over the past few decades has revolutionized our understanding of planetary systems. We now know that planets are common, that most stars have them, and that they come in varieties we never imagined, based solely on our own solar system. There are hot Jupiters, gas giants orbiting so close to their stars that their atmospheres are heated to thousands of degrees. There are super-Earths, rocky planets larger than Earth, but smaller than Neptune. There are ocean worlds entirely covered in deep global oceans. There are lava planets so close to their stars that their surfaces are molten. The diversity is staggering and continues to grow with each new discovery. This diversity extends to the stars themselves. Stars range in mass from less than 1/10 the mass of the Sun to over 100 times as massive. They range in luminosity from dim red dwarfs emitting a tiny fraction of the Sun's light to brilliant blue supergiants shining with the luminosity of 1,000,000 suns. They range in size from white dwarfs, about the size of Earth, to red supergiants so large they could engulf the inner solar system. They range in temperature from a few thousand degrees to tens of thousands of degrees at their surfaces, and from millions to billions of degrees in their cores. Each type of star has its own life cycle, its own destiny. The smallest, dimmest red dwarf will burn for trillions of years, far longer than the current age of the universe. Medium-sized stars like the Sun will shine for billions of years before swelling into red giants, shedding their outer layers and leaving behind dense white dwarf cores. The most massive stars will burn bright and fast, exhausting their fuel in just a few million years before exploding as supernova and leaving behind neutron stars or black holes. These stellar remnants, white dwarfs, neutron stars, and black holes, represent extreme states of matter. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a purely quantum mechanical effect. A white dwarf packs about the mass of the Sun into a sphere the size of Earth. Neutron stars are even denser, packing more than the Sun's mass into a sphere just 20 kilometers across. At these densities, matter exists in states that cannot be reproduced in any laboratory on Earth, states where atomic nuclei are crushed together and electrons and protons merge to form neutrons. Black holes represent the ultimate endpoint of gravitational collapse. When a massive star exhausts its fuel, its core collapses catastrophically. If the core is massive enough, no known force can stop the collapse. The core shrinks past the point where it becomes a neutron star, continuing to collapse until it becomes a point of infinite density called a singularity, surrounded by an event horizon from which not even light can escape. Black holes are regions of space-time so warped by gravity that they effectively cut themselves off from the rest of the universe. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes with masses millions to billions of times the mass of the Sun. How these monsters formed is still not entirely understood. They might have grown by consuming gas and stars over billions of years, or they might have formed from the direct collapse of massive gas clouds in the early universe, or they might have grown through mergers of smaller black holes. Regardless of their origin, supermassive black holes play a crucial role in galaxy evolution, regulating star formation through feedback processes and shaping the large-scale structure of their host galaxies. Now let us consider the composition of the universe, another dimension of its vastness and mystery. When we tally up all the different forms of matter and energy in the universe, we find that ordinary matter, the stuff we're made of, accounts for only about 5% of the total. The rest is divided between dark matter, which makes up about 27%, and dark energy, which accounts for about 68%. Dark matter reveals itself only through its gravitational effects. It does not emit, absorb, or reflect electromagnetic radiation, making it invisible to telescopes operating at any wavelength. Yet its presence is undeniable. Galaxies rotate too fast for the visible matter they contain to hold them together gravitationally. Galaxy clusters are more massive than their visible matter suggests. The gravitational lensing of light from distant objects indicates the presence of invisible mass. All these observations point to vast quantities of dark matter pervading the universe. What is dark matter made of? This is one of the great unsolved mysteries of modern physics. It cannot be ordinary atoms, which would interact electromagnetically and be visible. It cannot be neutrinos in sufficient quantity, as they are too light and move too fast to clump gravitationally as dark matter does. The leading candidates are exotic particles predicted by extensions of the standard model of particle physics, particles that interact only through gravity and possibly the weak nuclear force. Decades of experimental searches have sought these particles, but none have been definitively detected. The nature of dark matter remains unknown. Dark energy is even more mysterious. Unlike dark matter, which clumps gravitationally and helps hold galaxies and clusters together, dark energy appears to be uniformly spread throughout space, even in the voids between galaxies. Its effect is not to attract, but to repel, driving the acceleration of cosmic expansion. The simplest explanation for dark energy is that it is the energy of empty space itself, what Einstein called the cosmological constant. Quantum field theory predicts that even empty space should have energy, but the predicted value is many orders of magnitude larger than what we observe. This discrepancy, known as the cosmological constant problem, is one of the worst mismatches between theory and observation in all of physics. The fact that 95% of the universe is composed of dark matter and dark energy, substances we do not understand, is deeply humbling. It tells us that for all our progress, our knowledge of the universe is profoundly incomplete. The visible universe, the stars and galaxies we can see, represents only a tiny fraction of what exists. Most of the universe is dark, invisible, known only through its indirect effects on the small fraction we can observe directly. Yet even this small fraction, the 5% that is ordinary matter, displays incredible richness. Ordinary matter is made of atoms, which in turn are made of protons, neutrons, and electrons. Protons and neutrons are themselves made of quarks, bound together by the strong nuclear force. This hierarchical structure, from quarks to nucleons to atoms to molecules to the vast array of materials and substances we encounter, arises from the interplay of the fundamental forces of nature. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern all physical interactions in the universe. Gravity, though by far the weakest, dominates at large scales, shaping the orbits of planets, the structure of galaxies, and the evolution of the universe as a whole. Electromagnetism binds electrons to nuclei, creating atoms, and governs chemistry, allowing atoms to combine into molecules. The strong force binds quarks into protons and neutrons and holds atomic nuclei together. The weak force is responsible for certain types of radioactive decay and plays a crucial role in the nuclear reactions that power stars. The unity and universality of these forces is remarkable. The same laws that govern the fall of an apple on Earth govern the orbit of galaxies around each other. The same electromagnetic force that makes a compass needle point north also holds your body together at the atomic level. The same weak force that allows the sun to shine through nuclear fusion also governs the decay of radioactive elements in Earth's crust. The universe is one system, governed by a small set of fundamental principles that apply everywhere and at all times. This unity suggests a deeper simplicity underlying the apparent complexity. Physicists have long sought a unified theory, a single framework that would encompass all the fundamental forces and particles. Grand unified theories attempt to unify the strong, weak, and electromagnetic forces. Theories of quantum gravity attempt to unify quantum mechanics with general relativity, bringing gravity into the quantum fold. String theory and loop quantum gravity are leading candidates for such a theory, though neither has been experimentally confirmed. The quest for unification continues, driven by the intuition that the universe, for all its complexity, is at heart simple and elegant. Let us now contemplate the universe from yet another perspective, as an information processing system. Information theory, developed in the mid-20th century, provides a framework for quantifying information and understanding how it flows and transforms. Applied to the universe, this framework reveals fascinating insights. The observable universe contains an enormous amount of information. Every particle, every field configuration, every pattern of matter and energy represents information. If we wanted to specify the exact state of every particle in the observable universe, we would need an incomprehensibly large amount of data. This information is not static, but constantly flowing and transforming. Particles collide and interact, fields evolve, structures form and dissolve. The universe is an immense information processing system, constantly computing its own evolution through the laws of physics. But information in the universe is not uniformly distributed. Some regions contain more information than others. A region of empty space contains relatively little information. It is nearly uniform and can be described with a simple specification. A galaxy with its complex distribution of stars and gas contains far more information. A planet with a biosphere contains even more, as living systems are characterized by highly organized, information-rich structures. Life, in particular, represents a concentration of information and complexity. A single cell contains vast amounts of information encoded in its DNA, in the configuration of its proteins, in the organization of its membrane and organelles. This information is not just passively stored, but actively used and propagated. Cells read their DNA to produce proteins, repair damage, reproduce, adapt to their environment. Life is an information processing phenomenon, and the evolution of life over billions of years can be seen as an exploration of the space of possible biological information structures. The human brain represents perhaps the most complex information processing system we know of. With roughly 100 billion neurons, each connected to thousands of others, the brain is a network of staggering complexity. It processes sensory information, stores memories, generates thoughts and consciousness. The fact that such a system can arise from the same matter and forces that govern stars and galaxies is one of the most astonishing aspects of the universe. Matter, organized in the right way, can become conscious, can think about itself, can ponder its own origins and nature. This connection between information, complexity, and consciousness points to a deep relationship between the physical universe and the mental realm. Consciousness is not separate from the physical world, but arises within it, emerging from physical processes when they reach sufficient complexity. We are part of the universe, and when we think about the universe is thinking about itself through us. This is not mysticism, but a straightforward consequence of the fact that we are made of the same matter as stars and galaxies, governed by the same laws, products of the same cosmic evolution. The universe's capacity to produce complexity and consciousness from simple initial conditions is remarkable. The early universe was nearly uniform, just a hot soup of particles and radiation with tiny density fluctuations. Over billions of years, gravity amplified these fluctuations, creating structure. Stars formed, producing heavy elements. Planets formed, providing environments where complex chemistry could occur. On at least one planet, chemistry became biology. Simple replicators evolved into complex organisms, and eventually consciousness emerged. This chain of increasing complexity, from quantum fluctuations to conscious thought, spans the entire history of the universe and all scales of organization. Now let us consider the ultimate fate of the universe, for the question of how big the universe is cannot be separated from the question of how long it will last and how it will end. The future of the universe depends primarily on the nature of dark energy. If dark energy remains constant, as current observations suggest, the universe will continue expanding forever, with the expansion accelerating over time. This scenario leads to what cosmologists call the Big Freeze or heat death. In this future, star formation will gradually cease as galaxies exhaust their gas supplies. The stars that exist will burn through their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. The universe will become darker and colder as these remnants slowly cool, radiating away their heat into the expanding void. Eventually, even these remnants may decay. Protons, if they are not absolutely stable, might decay on timescales of many tens of orders of magnitude of years, causing even dead stars to slowly evaporate. Black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incredibly long timescales. By the time the universe reaches ages measured in googolls of years, far, far longer than we can meaningfully express, it will consist of dilute radiation and occasional particles, spread across an ever-expanding space, approaching but never quite reaching absolute zero in temperature. This is not a dramatic end like a big crunch or big rip, but a slow, asymptotic approach to emptiness, a fading into darkness and cold that never quite completes but approaches ever closer to nothingness. This fate seems bleak from a human perspective, but it is also peaceful, a gradual return to simplicity after billions of years of complexity. The universe will not be destroyed, but will relax into its lowest energy state, a vast, cold, dark expanse with only quantum fluctuations occasionally disturbing the silence. All the structure and complexity that emerged over cosmic history, all the galaxies and stars and planets and life will have dissolved, returned to the fundamental simplicity from which they came. But this is not the only possible fate. If dark energy evolves over time, strengthening rather than remaining constant, the expansion of the universe could accelerate so rapidly that it tears apart gravitationally bound structures. This scenario, called the Big Rip, would see first galaxy clusters torn apart, then galaxies, then solar systems, then planets, and eventually even atoms, as the fabric of space expands faster than any force can hold structures together. This would be a violent end, a catastrophic disintegration occurring over a finite time, perhaps tens of billions of years in the future. Alternatively, if dark energy weakens over time, the expansion of the universe might slow and eventually reverse, leading to a big crunch. In this scenario, the universe would stop expanding and begin contracting, with galaxies falling back toward each other, eventually collapsing into a hot, dense state similar to the Big Bang, but in reverse. Whether anything could survive such a collapse, whether a new universe could emerge from the crunch, or whether it represents a true end to space and time, we do not know. Current observations favor the heat death scenario, with dark energy behaving like a cosmological constant and driving eternal accelerating expansion. But our observations span only a tiny fraction of cosmic time, and we cannot rule out evolution of dark energy on longer timescales. The ultimate fate of the universe remains an open question, one that future observations and better theoretical understanding may eventually answer. As we contemplate these vast timescales and ultimate fates, we are reminded again of the temporal dimension of cosmic vastness. The universe is not just large in space, but extensive in time, stretching from the Big Bang nearly 14 billion years ago to an unimaginably distant future, trillions upon trillions of years hence. We exist in a brief, bright interval, an era when stars shine and galaxies cluster, when complexity is possible and life can exist. Before this era was a much briefer period of hot, uniform simplicity. After this era will come an incomprehensibly long twilight of gradual decay and dissolution. Our existence in this particular epoch is not arbitrary. Life requires energy gradients, stable environments, and complex chemistry, all of which are available only during the era of stars and planets. We find ourselves in this era because only this era can produce and sustain beings like us. This is the anthropic principle. We observe the universe to have the properties it does because if it did not have these properties, we would not be here to observe it. The universe's apparent fine-tuning for life is explained not by design but by selection. We necessarily find ourselves in a region of space and time compatible with our existence. This anthropic reasoning extends to the question of size. The universe must be at least as large as the observable universe for beings like us to exist, because the processes that led to our existence, the formation of stars and galaxies, the synthesis of heavy elements, the evolution of planetary systems and life, require billions of years to unfold. During those billions of years, the universe has been expanding, growing to its current vast size. A smaller, younger universe would not have had time to produce observers. The size of the universe is thus related to its age, and its age is related to the time needed to produce complex structures like galaxies, stars, and life. So when we ask how big the universe is, we are also asking how old it is and how long it took for conditions suitable for observers to arise. The universe is big because it is old, and it is old because creating observers takes time. This connection between size, age, and the possibility of existence is one of the deep insights of modern cosmology, linking the largest scales to the emergence of life and consciousness. Let us now return to the human scale and consider what all this vastness means for us as individuals and as a species. We are small, unimaginably small compared to the cosmos. A human being is about 2 meters tall. The Earth is about 13,000 kilometers in diameter, over 6 million times larger than a human. The Sun is over 100 times larger than Earth. The distance to the nearest star is over 200,000 times the distance from Earth to the Sun. The Milky Way is over 100,000 light years across, containing hundreds of billions of stars. The observable universe is nearly 1 billion times larger still. These comparisons can be overwhelming. It is easy to feel insignificant when confronted with such scales. If the universe is so vast and we are so small, do we matter at all? Is human life meaningful in a cosmos of such incomprehensible extent? The answer, I believe, is yes. Meaning is not a matter of size but of significance, not of scale but of value. A human life is meaningful not because humans are large but because humans are conscious, capable of experience, of love, of understanding, of creating beauty and meaning. The universe is vast and mostly empty, but we are not. We are concentrations of complexity and consciousness, rare and precious in a cosmos that is, as far as we know, mostly unconscious and devoid of life. Moreover, we are connected to the cosmos in profound ways. We are made of atoms forged in stars that died billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in stellar cores and scattered into space by supernova. We are literally made of stardust, our bodies composed of material that has been part of the cosmic cycle for billions of years. When we look up at the stars, we are seeing distant suns, but we are also seeing our own origins, the furnaces where our atoms were created. We are also participants in the universe's evolution. Through science, we have come to understand our cosmic context, to see how we fit into the larger scheme of things. Through technology, we have begun to extend our reach beyond Earth, sending spacecraft to other planets, placing telescopes in orbit, listening for signals from other civilizations. Through culture and creativity, we give meaning to our existence, creating art and music and literature that express our experience of being alive in this vast cosmos. And perhaps most significantly, we are the universe becoming conscious of itself. We are part of the cosmos, not separate from it, and through us, the universe reflects on its own existence. When we ask how big the universe is asking this question of itself through us. When we marvel at cosmic vastness, the cosmos is marveling at itself. This is a remarkable role, even if we are small and brief. We are witnesses to existence, participants in the cosmic story, temporary but genuine manifestations of the universe's capacity for self-awareness. So how big is the universe? We have explored this question from many angles: spatial extent, temporal duration, structural complexity, information content, the range of scales from quarks to superclusters, the diversity of phenomena from black holes to biospheres. We have seen that the observable universe is about 93 billion light-years in diameter, containing trillions of galaxies and incomprehensibly many stars and planets. We have seen that the entire universe may be much larger, possibly infinite, with regions forever beyond our observational horizon. We have seen that the universe spans many orders of magnitude and scale, from the smallest particles to the largest structures, all connected through physical law. We have also seen that size is not just a number, but a relationship. Depending on how we measure, from what perspective we view, in what reference frame we reside. We have seen that the universe is not just large but also old, not just extensive but also evolving, not just vast but also rich in structure and complexity. We have seen that asking how big the universe is leads us into deep questions about time, space, causality, information, consciousness, and the ultimate fate of all things. The universe is bigger than we can fully comprehend, yet we have managed to measure and map and understand significant portions of it. The universe is mysterious, yet we have uncovered many of its secrets through patient observation and bold theorizing. The universe is vast, yet we are part of it, made of its matter, shaped by its laws, products of its evolution, participants in its story. As you rest now, let these thoughts settle into your mind. The universe is immense, stretching from the quantum foam at the Planck scale to the cosmic horizon billions of light-years away. It is ancient, nearly 14 billion years from the Big Bang to now, and it will endure for incomprehensible ages into the future. It is complex, organized hierarchically from fundamental particles to atoms to molecules to stars to galaxies to the cosmic web. It is mostly dark, composed primarily of dark matter and dark energy we do not understand. It is mostly empty, vast voids separating the islands of matter and energy we call galaxies and stars. But it is also beautiful. It has produced stars that shine for billions of years, galaxies that spiral in the darkness, planets where complex chemistry can occur. It has produced life, consciousness, beings capable of wondering about their place in the cosmos. It has produced you, a temporary arrangement of atoms that can think and feel and ask questions about existence itself. The universe is as big as it needs to be to make this moment possible, this moment of awareness and wonder, this moment where conscious beings contemplate the vastness that contains them. How big is the universe? Big enough to contain galaxies and stars and planets and life. Big enough to inspire awe and curiosity. Big enough that we will never fully comprehend it, but not so big that we cannot understand significant parts of it. Big enough to remind us we are small, yet intimate enough that we are part of it, not separate from it. You are a child of the cosmos, made of star stuff, shaped by billions of years of cosmic evolution. You are temporary, brief, a flicker of consciousness in the vast darkness. But you are also real, and your existence, however brief, is part of the universe's story, a genuine and meaningful expression of what the cosmos can do when matter organizes itself with sufficient complexity. Rest in that knowledge. Wonder at the vastness, appreciate the beauty, and know that you are home, part of the only universe we have ever known, vast and mysterious and utterly amazing in its capacity to produce beings who can ask, how big is the universe? And in asking, make the universe a little more aware of its own existence. There is one more dimension worth exploring before we close this contemplation, and that is the experiential, subjective dimension of cosmic vastness. The universe is not just an objective reality to be measured and catalogued, but also an experience, something we encounter through our senses and our imagination, something that affects us emotionally and philosophically. When you step outside on a clear, dark night and look up at the stars, you are seeing the universe directly, without mediation. The photons entering your eyes have traveled across space for years, decades, centuries, or millennia, carrying information about distant suns. These are the same photons that left those stars long ago, and they have traveled unimpeded through the vacuum of space to reach your retina at this precise moment. In a very real sense, you are touching the stars when you see them, connected across space and time by threads of light. This direct connection to the cosmos is ancient and profound. Our ancestors looked up at the same stars, though configured slightly differently due to the slow motion of stars through the galaxy. They wondered about these lights in the sky, created myths to explain them, used them for navigation and timekeeping. The stars were woven into human culture and consciousness long before we understood what they actually were. Even now, with all our scientific knowledge, the sight of a star-filled sky can inspire wonder and awe, can make us feel both small and connected to something vast. The emotional response to cosmic vastness varies from person to person. Some find it frightening or overwhelming, the sheer scale inducing a kind of existential vertigo. If the universe is so large and we are so small, it can seem that we do not matter, that our lives are insignificant, that nothing we do makes any real difference in the grand scheme of things. This feeling, sometimes called cosmic nihilism, can be paralyzing, draining life of meaning and purpose. But others find cosmic vastness liberating or inspiring. Knowing that we are part of something so much larger than ourselves can provide perspective on everyday worries and troubles. The things that stress us, the social anxieties, the minor frustrations, the petty concerns, can seem less important when viewed against the backdrop of the cosmos. This is not to say that personal problems do not matter. They matter very much to the people experiencing them, but the cosmic perspective can help us keep them in proportion, can remind us that there are scales of experience beyond the human, scales on which our troubles are invisible. Some find meaning not despite cosmic vastness, but because of it. The fact that the universe is so large and old that it took billions of years of cosmic evolution to produce us, that we are rare and perhaps unique in our corner of the cosmos, can make existence seem more precious, not less. We are not meaningless specks, but improbable wonders, complex organizations of matter that can think and feel and create meaning. The universe did not have to produce conscious observers, but it did, and we are here, and that is extraordinary. There is also a philosophical tradition that finds in cosmic vastness a kind of spiritual or transcendent dimension, the feeling of connection to the cosmos, the sense of being part of something much larger than oneself, can resemble religious or mystical experiences. Some people describe looking at the stars and feeling a sense of unity with the universe, a dissolution of the boundary between self and cosmos. This is not necessarily a supernatural experience, but can be understood naturalistically as a recognition of our deep connection to the physical universe, a visceral understanding that we are not separate from nature, but part of it. Science does not diminish these experiences, but enriches them, knowing that we are made of stardust, that the atoms in our bodies were forged in stellar cores, that we are the product of nearly 14 billion years of cosmic evolution, adds depth and meaning to our sense of connection. We are not just metaphorically connected to the stars, but literally made of the same substance, governed by the same laws, products of the same processes. This knowledge does not make the universe cold or impersonal, but reveals it as a place of deep interconnection and astonishing creativity. The question of how big the universe is thus becomes not just a scientific question, but an existential one. It touches on who we are, what our place is, how we should understand our relationship to the cosmos. Different answers to this question, different ways of holding the scale of the universe in our minds, can lead to different philosophies of life, different ways of finding meaning and purpose. Some find meaning in exploration and discovery, and pushing the boundaries of human knowledge, and learning more about the universe and our place in it. Science, in this view, is not just a method for acquiring factual knowledge, but a profound human activity, an expression of our curiosity and our desire to understand. Every new discovery, every measurement that extends our knowledge of cosmic scales is an achievement worth celebrating, a testament to human ingenuity and persistence. Others find meaning in creativity and expression, in using our brief time to create beauty, to connect with others, to leave something behind that enriches human culture and experience. Art, music, literature, philosophy, these are ways we respond to existence, ways we process our experience of being alive in a vast cosmos. They do not require that we understand the universe scientifically, but they can be deepened by such understanding, can incorporate cosmic themes and perspectives. Still others find meaning in ethics and compassion, in recognizing that if we are rare in the cosmos, if conscious beings are precious and improbable, then we have a responsibility to care for each other and for the biosphere that produced us. The cosmic perspective can inspire ethical behavior, not through fear of cosmic judgment, but through recognition of our common humanity and our shared home in a universe that is, as far as we know, mostly empty and lifeless. These are not mutually exclusive approaches. Most people find meaning through a combination of understanding, creativity, relationships, and values. The cosmic perspective can inform all of these, providing a framework for thinking about what matters and why. The question of how big the universe is becomes a question about how we fit into it, how we make sense of our existence within such vastness, how we live meaningful lives given our place in the cosmic order. Let us now consider how the perception of cosmic scale has changed throughout human history. For our understanding of the universe's size has evolved dramatically over time. For most of human history, the cosmos was thought to be much smaller than we now know it to be. Ancient cosmologies typically placed Earth at the center, with the sun, moon, planets, and stars revolving around it in a series of celestial spheres. The stars were thought to be fixed on the outermost sphere, perhaps a few thousand kilometers away, certainly no farther than the distance to the sun or moon. This geocentric cosmos was small and comprehensible, human-scaled in a way. The entire universe might span a few million kilometers, tiny by modern standards. It was also purposeful, designed for human habitation, with Earth at the center and the celestial bodies moving in perfect circles, because circles were considered the most perfect shape. This was a cosmos that made sense to human intuition, that reflected human values and aesthetics. The Copernican revolution shattered this cozy picture. By placing the sun at the center and Earth as one planet among others, Copernicus began the process of displacing humanity from the center of the cosmos. Galileo's telescopic observations revealed that the moon had mountains, that Jupiter had moons, that the Milky Way consisted of countless individual stars. These discoveries suggested that the universe was larger and less centered on humanity than had been thought. As telescopes improved and observational astronomy advanced, the scale of the cosmos continued to expand in human understanding. The distance to stars was measured, revealing them to be unimaginably far away, light years rather than kilometers. The Milky Way was recognized as a vast collection of stars, and eventually other galaxies were discovered beyond it, island universes in their own right. Each new discovery pushed the boundaries of the known universe outward, making the cosmos larger and humans proportionally smaller. This expansion of cosmic scale has continued to the present day. We now know that the observable universe is nearly 1 billion kilometers across, containing trillions of galaxies, each with billions of stars. And beyond the observable universe, there may be infinitely more, regions forever beyond our view. The universe has grown from a human-scaled cosmos of a few million kilometers to an incomprehensibly vast expanse that dwarfs not just humanity but even our entire galaxy. This expansion of scale has profound philosophical implications. Each step in the growth of the cosmos has been a lesson in humility, a realization that we are not as central or special as we once thought. We are not at the center of the universe. Our planet is not unique. Our sun is an ordinary star. Our galaxy is one among trillions. This progressive displacement, sometimes called the Copernican principle, has forced us to abandon anthropocentric views of the cosmos and recognize that the universe is not made for us or about us. It simply is, and we are fortunate to exist within it. The universe is vast beyond comprehension, containing trillions of galaxies across nearly 100 billion light years. Yet this immensity liberates rather than diminishes us. We are free to create our own meaning. Though physically small, our minds transcend size through science and reason, allowing us to grasp cosmic scales we'll never witness and understand the universe's structure from the Big Bang onward. The universe is big enough to contain everything we know, inspire endless wonder, and make us feel both small and part of something grand. It is exactly as big as it needs to be to contain this moment, this thought, this question, and that is enough.